I'll begin. Holy Father, we thank you for this day. I thank you for the students. Just ask you to bless our work today, Lord. In your name I pray. Amen. Okay, so I've actually already typed up Chapter 5. So Chapter 4 is on limits, and so I have taken a somewhat, if you really want to strip down what I've done in Chapter 5, it's essentially to describe how you take limits of functions on Rn. And with respect to the usual so-called metric topology. And all that means is that we're judging open, we're judging the ideas of open and closed and so forth on the basis of the Euclidean norm, which is what you're probably already familiar with. In other words, that the length of a distance between 2 points is judged by the square root of the sums of the differences of the components, So just the usual distance formula you learned back in middle school or whatever, except in n dimensions. That's the basis for everything here. But just want to forge ahead here. So definition, if we have f going from some subset of A to A, all right, be a function, and z naught a limit point of U. All right. Also, we're going to suppose that L is an element of A. Now, what's A for us here? A as a point set is just equal to Rn, all right? But we're thinking of it as an algebra, so it's got, a multiplication. Actually, that has almost nothing to do with what we're doing right now. We can define limit, open, boundary point, all that stuff. It's got nothing to do with the multiplication. The reason I'm putting A here is just because that's our main application. We're looking at functions on algebras, all right? So that's why I'm talking about the definition in a sense, but from a pure perspective, you could just talk about functions from Rn to Rn, and almost everything I'm about to say you could still say, okay? Anyway, so let Z be an element of A. Here's the deal. We say the limit as Z goes to Z naught of f of Z is equal to L if for each epsilon greater than 0, there exists a delta greater than 0 such that Z in A with 0 less than the norm of Z minus Z naught less than delta implies that the norm of f of Z minus L is less than epsilon. We say f is continuous at Z naught if the limit as Z goes to Z naught of f of Z is equal to f of Z naught. So for this last sentence to make sense, what else do you need to know about the limit point Z naught? Where does it have to be? If I'm going to calculate f of Z naught, what do we have to be able to say about Z naught? It has to be in the domain of the function, right? But I would draw your attention to the fact that this definition, and what are we defining here? We're defining the limit, right? Defining the limit. Notice that the limit point here, Z naught, doesn't have to be in the domain of the function we're taking the limit of, right? It has to be a limit point. Now, what's that mean? So there could be like a hole here, right? Be like a hole in the domain. That could be where Z naught is, right? what was the definition of limit point? We said that if you look at any open neighborhood around the point, there has to be what? There has to be points inside the domain of the function, right? I mean, I defined it carefully in section 4.2, I believe. We say y in A is a limit point if every open ball centered at y contains points in the complement of S by y. So if there's a limit point of S is a point such that if you look at, I mean, if I have y and this is S, then y is a limit point if you look at S with y removed, and if any open set around y has points in S. Well, not has points in S is what? Wait a minute. Goodness gracious. Where did I? Every open ball contains points in. It doesn't say that every open ball is contained in there. It says every open ball contains points in. So like this open ball out here centered around y, it's not contained in S, but it contains points in S, right? So it's the limit point. Yes, Sam?
In the definition when you say such that Z is in A, blah, 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 should that be Z is in U? Because otherwise it can't.
Oh, yeah. Thank you. That is a more, a considerably more substantial correction to what I'm saying than my blathering on about what a limit point is. All right. Anyway, a limit point is a point in which taking the limit makes sense. Is another. I mean, that's why it's called limit point, right? So the picture of this is you're trying to, over here, we've got the L, the alleged limiting value, right? And you're taking an open ball around that. You have to be able to, for any epsilon, like this, you have to be able to find a delta over here so that when you look at the image of this, it fits inside this epsilon ball, right? You have to be able to produce a delta to make that happen. Intuitively speaking, if your function has like a jump, right? If it jumps, then you might not be able to do that. And then such a function would be called discontinuous and so forth. All right, enough. This is, of course, just the definition from Calculus 1, the epsilon delta definition for the limit, except what? We've replaced absolute value of a number with the norm in the algebra, right? But otherwise, it's the same definition. And there are properties, which I'll write over here. Try to get on with it here. So if we have functions, this is my theorem 4.32. And here it is. If we have that the limit as z goes to z naught of f of z and the limit as z goes to z naught of g of z. Suppose these are both elements of the algebra. In other words, that they both exist. And let's, in addition, suppose that c is a constant in the algebra. Then we have a few fun facts. First of all, what's the limit of a sum? What's that? Yeah, finally. Let's see here. Yeah, I know. I also usually miss. All right, limit z goes to z naught, but all right, so what's, so surprising this is not, yes? B, the limit as z goes to z naught of f of z star, g of z, is equal to the limit as z goes to z naught of f of z, algebra product times the limit of z goes to z naught g of z. C, the limit as z goes to z naught of a constant times the function, but the product here is the product in the algebra. Well, you can also pull out the constant from the limit and multiply it by the in the natural way like this. And then d, the limit z goes to z naught of f of z over g of z equals to the limit f of z over the limit g of z. Find z goes to z naught. Why didn't I just declare that we were going to write limit for limit that goes to z naught? I mean, I should just write lim, and why didn't I just write lim everywhere? Oh, poor planning on my part. Oh, goodness gracious. This is provided limit as z goes to z naught of g of z is where? Now, if we were working in the complex numbers, or if we're working in the real numbers, we just say non-zero there, because that's all you need for division to make sense. But in an arbitrary algebra, we need that it's not zero, and it's also not a non-zero zero divisor, right? In other words, we need that it's in the units. So we need that the limit is an element of the units of the algebra for that last limit law to make sense. All right? Now, if you think about it, if you have part B, you can easily get part C if you knew that the limit of a constant was just the constant again. Maybe I should prove that for you guys. Let's start out with that. Shouldn't take long. Let's let f of z equal to a constant for all z in A, right? Let epsilon be greater than 0. Choose delta equal to, I can't usually do this, but pick a number, any number. What do you guys want? 5 works. Great. Let z be an element of the algebra such that 0 is less than the norm of z minus z naught is less than delta, right? I guess I should also say let z be an element of A and let z naught be an element of A. All right. So this is assumed to be less than delta, all right? Consider the norm of f of z minus c. My claim is that the L in the the big L in the definition is just c here. The limiting value of the constant function is just the constant, right? And this is extremely silly. That is what? That's equal to the norm of c minus c, which is, by the way, the norm of 0, which is 0, which, of course, is less than epsilon. So that proves, thus, the limit of c as z goes to z naught is what? Is just c again, from the definition. What did 5 have to do with anything? Not a thing, right? But you see now that we have this, that part C is an immediate consequence of part B, right? If we have C, we get, if we have the thing I just did and B is true, then we get part C. Let's do one more of these and then I'll go on. How about the limit? I'd like to prove that the limit as z goes to z naught of z is equal to z naught, right? So let epsilon be greater than 0. Choose delta equal to, I'm going to let's fill in the blank, all right? let z naught be in the algebra, and suppose that the norm, that 0 is less than the norm of z minus z naught is less than delta for some z and z, right? And consider the norm of z minus z naught, right? So let me just emphasize that this is playing the role of f of z, and I'm claiming this is playing the role of L from my definition that I stated on the other board. Like logically, we're thinking of the function f of z equal to z, the so-called identity function on the complexes, and I'm thinking of the limiting value being z naught, right? So that's the role that these things are playing. So what you can fill in the blank for me. I want this to be less than epsilon, right? So that's less than delta, which, by the way, is what? In retrospect, what should we have made our delta? You may remember this from Calculus 1 here. Or not. How about epsilon, maybe? Yeah. So we're done. So we've shown that f of L minus f of x, f of z minus f of L has norm less than epsilon. Therefore, the limit as z goes to z naught of z is equal to z naught. Operationally, the really only difference here between this and what we do in Calculus 1 is that absolute value has been replaced with norm, right? So now, I said in the notes that I would show you the proof of part A in class, so let's do that, all right? Now that we've wet our whistle here with some kind of baby ones. And by the way, I'm never going to do anything as sophisticated as we do in Calculus 1 here. Like in Calculus 1, we teach you how to calculate the limit of quadratics using epsilon delta arguments, yeah? That's not happening here. We're going to use theory to calculate the limit of z squared. It's much easier. It was like an application of a lemma and a proposition. It's done. There's like no epsilons and deltas. So we do epsilons and deltas just to start, but soon we'll have theorems that will take over. All right. Okay, so let's prove part A. So we're given, we have that, let's say L sub f is equal to the limit of f of z, and L sub g is equal to the limit of g of z. Fine. Z goes to z naught. Z goes to... I'll stop grumbling. All right. You also have to write, I suppose. All right. So we're given that these things exist, right? All right. These are numbers in A, right? All right, great. Let epsilon be greater than 0. I would point out then that we can choose delta sub f, and we can choose delta sub g greater than 0, such that if 0 is less than the norm of z minus z naught is less than delta sub f, that implies that the norm of f of z minus L sub f is less than, well, something, fill in the blanks. And also, whenever 0 is less than the norm of z minus z naught is less than delta g, well, that implies that the norm of g of z minus L sub g is less than something. We're going to fill in the blank. All right. What's our goal? So let z be in A such that 0 is less than the norm of z minus z naught is less than delta, which is equal to the minimum of delta f and delta g. In other words, I want to have my cake and also my other cake, the two cakes being the two inequalities listed above. I want to have control over f. I want to have control over g at once. So I choose delta, which is the minimum of both deltas, to make both conditions that we're going to fill in the blank for be true. All right? What is our goal? Well, consider the norm of f plus g of z minus L sub f plus L sub g, right? We want to show that that is less than epsilon. If we can show that's less than epsilon, that proves part A, right? Because part A, in my current notation, is that the limit of f of, this is f of z plus f of z plus g of z, that this is equal to LF plus LG, right? That's what we're, you pan over for just a second. We're trying to show that, this is L sub f, this is L sub g. We're trying to show that that limit is LF plus LG, right? So to do that, we have to show that the norm, and I'm sorry, we can rewrite that. I'm so sorry. I should just write it f of z plus g of z. I was thinking about something else. That's fine. But let's regroup. Let's just regroup a bit. That's f of z minus LF plus g of z minus LG. Close norm. And let me add some parentheses for emphasis. We've got this difference of f and its limit, this difference of g and its limiting value rather. So one of the properties of norms that I said in like a 3-second period last time, I'm almost like blah, 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 about norms, and then we went on. But one of the things I about was that norms satisfy the triangle inequality. So the norm of a sum is less than or equal to the sum of the norms. In particular, here, this is less than or equal to the norm of f of z minus L sub f plus the norm of g of z minus L sub g. Right? So now you guys tell me, what should I fill in the blanks? What and why can I fill in those blanks? I'll put the y over here. Still got some room. I say we make this one epsilon over 2. And, using, let me give it a name. I don't want to write it again, star. And I say we make this one epsilon over 2 using star star. In other words, using that the limits of f and g separately exist. That means that I can choose delta to make the difference of f and its limiting value as small as I like. And likewise for g. And then if I let my delta be the minimum of both of those, then I get both of those being less than epsilon over 2, which gives me, of course, this is, less than epsilon over 2 plus epsilon over 2, which is also known as epsilon. Therefore, A follows. You should recognize this proof. This is exactly the same proof you were shown in Calculus 1 if you took it here with a responsible instructor. This is the proof we're supposed to show you in Calculus 1. I do this proof in Calculus 1. When Dr. Wang started teaching Calculus 1 many moons ago, well, not that many moons, but a few moons ago, on his first test, he asked students to prove this with epsilons and deltas. He didn't think he was being mean either. Now, I might do that, but I would tell students I was doing it ahead of time, So, yeah. Anyway, that's the proof which is missing from my notes. It's pretty standard, and there it is, all right? Now, the proof of the part B is technical for us. Part B is actually kind of tough to prove. Even in the complex case or the real case, the proof of the product rule for limits is a little bit involved. For us, it's kind of a lot involved, so I'm going to use the projector because, the things I do in this proof are not that important in the big scheme of things, and I want to show them to you and show you how you prove them. But in contrast, this is very much a possible next test question, right? What I'm about to show you on the projector would be a ridiculous thing to put on a test. Because a lot of it's about like, how much linear algebra thinking is there in this proof? Zero. Pretty much zero linear algebra thinking in this proof. How much linear algebra thinking is there in the proof I'm about to show you? It's about 80% linear algebra thinking. Something like that. 10%? Easy 10. Find my laser. So I've already written chapter 5, you guys. I just need to like post it. I'm sorry I haven't done that yet. I was actually planning to do that last night, and then apparently I fell asleep. So I have no memory of this, but it happened. And so have you guys figured out which love language you speak? No? Hard segue. Yeah, my love language is linear algebra. Is that in the book? The problem with you and me is we have a different idea of linear independence. I'll just never fit inside your span. I don't know. You can go further with this, I think. I'll leave the rest to Sam. I feel like I've given him the start he needs to tell a horrible joke. All right, so again, the thing we're trying to prove right now is that the limit of the product is product of limits. And so what I do is I take a function, and over the algebra, it has n component functions, all right? Each one of these is real valued. And the vector limit theorem of advanced calculus says that the limit of a vector exists if and only if the limit of each component of the vector exists. So you can break it down and do component by component. That's one point. Now, if you look at this product function f times g, which is f of z times g of z, we can write it as a sum of the component functions weighted against the structure constants. In particular, fg is equal to the sum over ij and k ranging from 1 to n of the structure constants Cijk times Fi, Gj, and Ek being the standard basis for us, all right? So the kth component function of the product is just the structure constants weighted against the product function, the components of f and g, respective, like this. Now the limits of Fi and Gj are given since we're assuming the limit of f and limit of g exists, so we know what these limit to. They limit to numbers which are given, whatever they are. And so then we can calculate. The limit as z goes to z naught of the kth component function is the limit as z goes to z naught of this mess. But this is nothing more than an ordinary product and sum of real numbers and real valued functions. But the pesky thing is that their domains are in the algebra. All right, so there's something new here. But first of all, we proved already that we can pull the constant out of a limit, right? I actually just proved that in class. If you combine what I just did with what I did before about the limit of a constant being a constant, right? So that's by what I already did in class today. And then this right here, I need a lemma, that the limit of two so these are real valued. Their domain is the algebra, but their range is just real numbers, all right? In contrast, the theorem is about functions which go from the algebra to the algebra. So like the thing we're trying to prove is about algebra valued functions. This lemma is for real valued. It's for the component functions of the algebra function. So by a lemma, this is equal to the product of the limits. And then you can use the vector limit theorem. The vector limit theorem says that the limit of the ith component function is the ith component of the limit of the vector, and vice versa for g. And then by the same algebra I just did, this is nothing more than the kth component of the product of the limit of f and limit of g, and that proves it, since k was arbitrary. It proves it modulo lemma 1. So lemma 1 is this. If we have a subset of A, and we've got functions fi and fg, gj, where z naught is the limit point of u, and the limit of z naught equals z naught of fi is li, and the limit of z goes to z naught of gj is mj, then the limit of the product of fi and gj as z goes to z naught is just the product of li and mj. Now these are just ordinary garden variety real numbers, right? So anyway, that we've reduced it to that lemma, and you have homework, yes? So maybe it's a homework problem, yes? Now, the homework, I did not just leave you out to dry. I gave you a link to the proof of that lemma in the case of real numbers. So if you just look at functions from reals to reals, prove that the limit of the product is the product of the limits. Even in the case of just real valued functions of a real variable, that proof is kind of delicate, and it requires some kind of careful argument. But there's a standard argument that can be given. I actually share with you a link to such a standard argument. It is my belief that you should be able to modify that standard argument because the range is absolute value. That's the norm in the range. But the domain has just the regular proof has the domain having absolute value arguments, right? So I think if you just take the arguments in the domain and replace absolute value with norm, that will give you the proof of lemma 1. I'm pretty sure. So I've tried to give you a lot of help with that lemma 1 in the way I was just describing. Lemma 2 says that if we have, the limit of g is in the units, then the limit of g inverse is g inverse, like that. And if I have that lemma 2, it's easy to prove. It's easy to prove part D, because then we can use the product in part B rather. And so the limit of this is the product of the limits provided they exist, which then gives us the quotient of the limits in that way. So the real question is, why is lemma 2 true? That rests on something, yet another theorem about limits, which you may or may not remember from Calculus 1, which is the composite limit theorem. Right? If you have a continuous function, you can pull the limit inside the argument, right? Like we use this in the calculation of L'Hopital's rule when we do stuff like we pull the limit inside the exponential sometimes, right? Because exponentials everywhere are continuous. But anyway, here's the limit law. Supposing that f is continuous at the necessary point at the limit of z goes to z naught of g of z, in particular, let's see here. So I need that if the limit of g is equal to w naught, I need that f is continuous at w naught. In that case, I can pull the limit as z goes to z naught of this inside like so, and this is the composite limit theorem. So if you have that, then it's easy to get lemma 2, because you can just let the f of z be the 1 over z function, which is going to be continuous on the units. This could be proved, but I haven't proved it, but you could prove it, yeah.
So should we focus on the lemmas and try to understand that for later homework?
Well, I would say 2 things. Make sure you understand the proofs that I did in class. I did 3 of them, right? Those should all be ones you get. I mean, knowing the definition is that's very important. I don't think lemma 2 is super important. I'm not super wedded to lemma 2. I mean, it wouldn't be bad if you worked it out. There's a gap in my thinking here. I haven't actually proved that 1 over z is continuous. I mean, it is. Where is it continuous? 1 over z is only continuous away from the 0 divisors in the algebra. Actually, that's an interesting homework problem I have not yet assigned. Sometimes that can be reinterpreted as a test question, so you're not totally off base. Anyway, moving on. So the homework, though, I've tried to give you guys homework which is pretty concrete in the sense that the homework is largely about, like I've asked you homework questions that are like the topological questions in the homework about like open set, boundary point, those kinds of terms. They're almost all in the context of complex numbers. And then I've just taken problems from Fisher because I think those will be helpful for you to really take to heart what terms like open, connected, and so forth like that means, yeah? Let's see here. Finally, continuity. I define continuity at a point in the definition I wrote on the board. what would we mean by continuity on a set? What would that mean? Continuity of a function on a set means that it's continuous at each point in the set. That's all. Yeah? And we also have a notation, C upper 0 of U, that's the set of continuous functions on U. All right. So in short, if you look at the theorem that I showed you, it's easy consequence that if we have f and g are continuous functions, then f plus g, f times g, and I'm missing a star right here, right? I meant to put a star right there, c times f, and of course f over g. These are all continuous, provided that g is well behaved. The conclusion basically is just what I tell you in Calculus 1, which is that a function built over formulas in the algebra is going to be continuous as long as the formula for the function makes sense, as long as it's well behaved, right? I mean, now there's subtleties, like the argument doubling back on itself. That we got to watch out for. That's kind of new, right? But we still have the trouble of division by 0. But now it's division by a 0 divisor is also a possibility. So I mean, our world's gotten a little bit bigger. But oh, look at it! I already did that today, didn't I? So, but here's the new interpretation: f of z equals to z is the function, and we showed that it has limit as z goes to z naught of f of z is f of z naught for arbitrary z naught, which shows you that the identity function is continuous on the whole algebra. So that's a function which is continuous on the whole algebra. And here's what I was talking about theory-wise. When I wanted you to show that z squared function is continuous, I'm not suggesting you do epsilons and deltas. No. I mean, you could, fine, if you really love it, great. But I prefer we use theory. So the limit of z squared is the limit of z times z. I use part B of the theorem to break up into the product of limits, but we prove that the limit of z is z naught, so we get z naught times z naught, which is z naught squared. And this little calculation right here shows that f of z equal to z squared is everywhere continuous over the algebra. For which algebra? All of them. Right. So I've written this chapter in such a way that we have proved theorems for all the possible algebras that we're interested in. So the hyperbolic numbers, the complicated numbers, the dual numbers of order 2, 3, 4, 5, 6, 7, 8, whatever, right? And the rest of it, all at once. You can also show things like the mapping z goes to real z or z goes to unreal part of z. Also z maps to the norm of z. These are all actually continuous on A. Those would not be hard to prove. And that brings us to chapter 5, which I have not yet posted. So I'm going to put this down and start writing some things on the board for you guys, all right? So, you know, guys, I'm not that interested in continuity in here. This is not a course about continuity. Continuity is necessary for the discussion, but our focus in complex analysis is really much more on calculus, either of the differential or the integral variety. All right? But to understand differential calculus, we have to first understand limits. That's true for calculus 1. It's true for, where are we? Calculus 5, 6? I don't know. It depends how many you took, right? But so here's the definition. So what I'm going to talk about here for the next about half hour or so of class, don't worry, not just today, real differentiability. So here it is, definition. If F is a mapping from, let's say, U, which is a subset of Rn, to Rm, all right? And, well, let me try to actually write down what I wrote in the notes. So if that's a function, we say that f is differentiable at a in u. Then we say f is differentiable at a in u. Now, I'm assuming that this u is an open set, okay? I should say that. Differentiable at a in u, if and only if there exists a linear function, or we could say linear transformation, that'd probably be better terminology, linear transformation. And here's a notation for it. D big F lower sub a, which is itself a mapping from Rn to Rm. No u here. This linear transformation is defined for all inputs from Rn, not just those in u. By the way, the name of this is called the differential. The differential of f at a, such that the limit as h goes to 0 of f of a plus h minus f of a minus the differential of f at a acting on h, all divided by the norm of h is equal to 0. This is what it means for a function from Rn to Rm to be differentiable at a point. So some terminology while I'm at it. This right here, guys, is the so-called Frechet quotient. The Frechet quotient. So in other words, we can say the function is differentiable if its Frechet quotient limits to 0, given the appropriate, differential. What do I mean linear transformation? What's that mean? That means we have the following. We have that dfa of like h plus k is what? It's dfa of h plus dfa of k. We have additivity, and we can pull out constants. That's what it means to be a linear transformation. Now, what did we learn about linear transformations? They can be represented by matrix multiplication, the formula, right? So, a little bit more here, furthermore. dfa of h is equal to the Jacobian of f at the point A times h, right? Where the Jacobian is the standard matrix of the differential at A. If this limit, if you cannot find a linear map dfa such that this limit exists, then the function is said to be not differentiable. Okay? So, otherwise it's not non-differentiable. Not every function is differentiable, right? Now, furthermore, this Jacobian matrix, we calculate it like follows. This is partial f. Actually, let me, if you don't mind, I'm going to just make a break and say generally the Jacobian matrix of f would be partial f, partial x, partial f, well, x1, partial f, partial x2, partial f, partial xn. This is how we calculate the Jacobian matrix for a function. Here, the function has the domain variables are x1 through xn. And here, to be more, another way you could write this would be it's a stack of gradient vectors, like it's the nabla f1, the transpose of that, nabla f2, the transpose of that, so forth and so on. How many component functions are there in F? I could write this. F is equal to F1, F2, Fm. There are M as in mummy, as contrasted to N as in nanu nanu, component functions. So there's M. You remember the gradient vector? Each row in the Jacobian matrix is a gradient vector of a component function. Each column is just a partial derivative of the function. I like to think in columns, personally. It's where linear algebra is happiest. Now, so what I'm going to prove in this chapter on real differentiation is an analog of what I just erased. Namely, that the sum of differentiable functions is differentiable. That the product of differential functions is differentiable in the appropriate interpretation. And there's also a chain rule for differentiable functions. All of these things are available. So this is not yet complex analysis. I'm just showing you in a nutshell what is real differential calculus for functions from Rn to Rm. You've seen from like R to R2, you've seen R to R3, you've seen some things about R2 to R2. All of these things are in the usual calculus sequence, but you never actually in the calculus sequence saw a proper treatment of differentiation of functions from Rn to Rm, where n and m could both be like more than one, right? And so that's what I'm trying to do here in the next half hour or so of lecture. It's not actually that bad. It's just unfamiliar. But let's an example here. I also have an axe to grind here. So I'm going to look at f such that from R2 to R2, but this one where I'm going to look at this. Well, let's say little f, actually, where little f of z equals to z squared is my formula for the function. I can't always do this, but I'm actually thinking of c is R2 for this function, right? And so like f of z equals z squared, what is that? That's f of x plus iy equal to, well, x plus iy squared, which is, by the way, x squared minus y squared plus 2ixy. I mean, that's the formula for this function in complex notation. What would the function be in real notation? In real notation, we've got f of x comma y equal to what? Equal to x squared minus y squared and 2xy if we go back to the, the real notation. So what's the Jacobian? What's the Jacobian for this function? It's the Jacobian of f. Well, I told you it should be partial f, partial x, and then partial f, partial y. That's the definition of the Jacobian in this context. All right? What is that? So you guys tell me what's that matrix? What do we got? Did you figure it out? Looks like we got a 2x and a 2y. And over here, partial f, partial y, minus 2y and 2x, right? Wait a minute. What is that? That is the matrix representation of 2x plus 2iy, right? Or in other words, that's the matrix representation of 2 times z. That's kind of interesting, isn't it? The Jacobian matrix of the squared function, it is the representation of the 2z function for complexes. That's neat. So I'll just tell you, try it out for the hyperbolic function, z squared. Same calculation, no minus. And again, you'll get the matrix representation of 2z. So most of my examples for Jacobians, as we're about to do next class, they're all going to be preaching this same pattern. This is a pattern we're going to see again and again, until we don't. At which point, maybe we'll figure out how we can define differentiability over an algebra. That's what's up next class. So thanks, guys. You can hit it.